The reality that we believe we know, the ground under our feet, the air that we breathe, the world that we see. But the more we delve, the stranger it becomes. Did you know that what we perceive as solid matter is mostly space? The atoms that compose everything around us are 999% space. Also, there is time, which is not a constant tick-tock in the background. Time can stretch, slow down, and even stop under the right conditions. So, how much of what we experience is real, and how much is just a construction of our mind? What if the reality in which we trust is only a shadow of something deeper, stranger, and infinitely more complex? What was reality for the first human beings? The answer was simple. Reality was what they could see, hear, touch, and smell. The world that surrounded them was interpreted through their senses, which guided them in their day-to-day. The whisper of leaves announced the arrival of a predator. The distant creak of a branch indicated the presence of prey, and the sensation of heat from a bonfire warded off the cold of night. This sensory reality was everything. Survival depended on it. Sight, hearing, touch, smell. These senses were the tools with which they knew their environment. But for them, reality was limited to what was accessible to direct perception. The invisible world beyond their senses was incomprehensible. Everything tangible became real. If a sound was heard, danger was near. If something was smelled, food could be found. If it could not be sensed, perhaps it did not exist. Survival was a continuous process of interpreting these sensory signals, often in life-or-death situations. Recognizing the difference between the roar of a predator and the whisper of wind could mean the difference between safety and death. The first human beings lived in a world where reality was directly related to their immediate needs: food, shelter, protection. For them, reality was not questioned. It was lived through experience. However, as society evolved, the concept of reality also changed. The question of existence and meaning began to extend beyond the immediate environment. What lies beyond the senses? What forces shape the world over time? The limitations of direct perception gave way to imagination and conjecture. This curiosity led to the birth of new ideas, a reality no longer tied to the physical world. The first human beings began to develop explanations for what they could not see or understand. Spirits, gods, and forces of nature became personifications of the unknown. Fire, lightning, and stars were attributed to forces beyond human control through mythology and beliefs. They created a broader reality that filled the gaps left by their sensory limitations. This cultural development marked a turning point in human thought. The journey of humanity, which began with the simple need to survive, has evolved into something far more complex. In one of the first philosophical explorations of reality, Plato presents this allegory of the cave. In this mental experiment, some prisoners have been confined in a cave all their lives, seeing nothing but shadows. The shadows are projected on the wall in front of them and are the only things they know. They confuse these flickering figures with reality itself. For them, the shadows are the only truth they know. But what would happen if they were freed from their chains and turn around? What would they see? Plato's allegory suggests that human perception is often limited. What we perceive as reality may be just a shadow of a deeper and truer existence. The path to understanding true reality, Plato argued, begins with questioning the world as we perceive it. Plato's allegory is not only a philosophical exercise, it is a profound commentary on the limits of human perception. We may think we see the whole picture, but we are often limited by the limits of our senses and our experience. Reality may, therefore, extend far beyond what we can directly observe in the physical world. Our understanding of reality underwent a significant change with the discovery of space-time in the early 20th century. Albert Einstein shattered the ancestral foundations of classical physics by demonstrating that space and time are not separate entities, as previously thought, but are intertwined in a single four-dimensional fabric, space-time. According to Einstein's general theory of relativity, Massive objects deform this fabric, creating what we experience as gravity. Planets revolve around the sun, not because they are attracted by an invisible force, but because the sun deforms space-time around it, creating a curved path for them. This revolutionary concept has completely changed our view of reality on a cosmic scale. Time is not absolute in Einstein's universe either. Time can stretch or compress depending on the speed at which one moves or its proximity to a more massive object. This idea, the dilation of time, means that time in itself is relative, which changes our perception of how reality unfolds. The scientific method has allowed us for centuries to reveal the layers of this reality. The classical mechanics developed by Newton gave us the tools to understand the movement of objects through the precise prediction of their trajectories. But as we began to delve into the nature of the universe, discoveries, especially in quantum mechanics and relativity theory, showed us that reality works in ways that common sense previously defined. The search for reality's basic components began thousands of years ago. In the 5th century BCC, the Greek philosopher Democritus suggested that everything in the universe is composed of tiny, indivisible particles, atoms. These atoms, according to him, are the fundamental components of all matter. This idea persisted for centuries until modern atomic theory took shape in the 19th century. Scientists like John Dalton began to provide empirical evidence that all matter was composed of atoms. These tiny particles, invisible to the naked eye, join together in various ways to form everything from the air we breathe to the stars. For a long time, it was thought that atoms were the most fundamental units of the physical world. But as our understanding deepened, we discovered that the atom itself could be divided into smaller particles. At the beginning of the 20th century, the discovery of subatomic particles, protons, neutrons, and electrons, demonstrated that atoms were not indivisible. These subatomic components opened the door to a completely new field of physics, quantum mechanics. Quantum mechanics offered a radically different view of reality at the atomic level. Particles behave in ways that defy classical physics rules. Electrons not only orbit the nucleus in orderly, predictable trajectories, but exist as probabilities. Their location is not fixed until they are observed. This strange behavior introduces the concept of superposition. Particles can exist in multiple states simultaneously until measured. At this level, the very nature of reality becomes uncertain. Classical physics taught us that the universe works like a precise machine with predictable cause and effect relationships. But quantum mechanics has shown that reality in its essence is governed by probabilities. This new understanding challenged the notion of a solid, deterministic universe and replaced it with one in which randomness and uncertainty prevail. As our understanding of the atom deepened, it became clear that even protons and neutrons, the components of the atomic nucleus, are not the most fundamental units. Within these particles, scientists have discovered quarks, elementary particles that bind together in combinations to form protons and neutrons. Alongside them, there are particles called gluons, which are responsible for binding the quarks together, acting as mediators of the strong force, the fundamental interaction that holds the atomic nucleus together. However, quarks are different from everything else in physics. They cannot exist individually, only in combinations bound by a strong force. This force is so powerful that trying to separate the quarks results in more quarks. It is a strange and complex system that continues to challenge our understanding of matter's fundamental structure. Subatomic physics, especially the study of quarks and gluons, has expanded the limits of our knowledge, making it even more unknown. Although the standard model of particle physics successfully explains many particles and forces in the universe, deeper questions remain. How do these particles interact at their most fundamental level? What are the true building blocks of reality? One of the boldest theories in the search for answers to these questions is string theory. This revolutionary idea suggests that the fundamental particles we observe, such as quarks and electrons, are not point particles, but tiny, one-dimensional strings. These strings vibrate at different frequencies, and their vibrations give rise to the different types of particles we observe. String theory is not limited to redefining particles, but suggests that these strings exist not only in the three familiar dimensions of space and the dimension of time, but also in multiple dimensions, perhaps 10 or 11. These additional dimensions are beyond our immediate perception. They're so rolled up that they remain hidden from view. If string theory is correct, then reality may be much more intricate than we ever imagined and extend into realms we have not yet observed. This leads us to the Copenhagen interpretation, one of the most famous philosophical foundations for understanding quantum mechanics, proposed by the physicist Niels Bohr. This interpretation is based on the idea that quantum particles do not possess certain properties until measured. Before observation, they exist only as probabilities. It is the act of measuring, the interaction with a conscious observer, that gives rise to reality. In other words, until a particle is observed, its state is fundamentally undefined, neither here nor there. However, not all physicists are satisfied with the Copenhagen interpretation. Some prefer the more radical many-worlds theory, first proposed by Hugh Everett. According to this interpretation, every time a quantum event occurs, every time the wave function of a particle collapses, the universe splits into two. In one, the particle follows one path, and in another, it follows a different path. Instead of converging, the universe splits into one in which the particle follows one path and another in which it follows a different path. Instead of converging on a single result, all possible results occur, but in different, branching universes. These parallel worlds exist simultaneously, each representing a different version of reality. The many-worlds theory offers an alternative to the idea that observation leads to the so-called collapse of reality. Instead, it argues that all possible realities exist, but we are only aware of the one in which we live. This is an amazing concept that expands the imagination and makes us think that reality is much more complex than what we see in everyday life. Whether we adhere to the interpretation of Copenhagen, to the theory of the many worlds, or to some other explanation, one thing is clear. At a quantum level, the rules of reality are not at all what they seem. Despite its elegance, string theory remains largely unproven. The theory operates at such small scales that modern technology cannot check its predictions, even with all our advances in subatomic physics. There is still much that we do not know. Quantum mechanics and general relativity, the two pillars of modern physics, remain incompatible, especially when it comes to explaining gravity at minimal scales. While the Standard Model describes the known particles and forces, it fails to fully explain dark matter, dark energy, and gravity, suggesting that there is much more to reality than we can perceive or measure. So the question arises, where are you now? Not in a physical or location sense, but in the sense of experience. Your consciousness is the lens through which reality is perceived, but what exactly is consciousness? Is it simply the result of electrical signals and chemical reactions in the brain, or is it something more, a fundamental part of reality itself? For much of modern science, consciousness has been understood as a byproduct of the brain, an emergent property that arises from the complexity of neurological processes in which billions of neurons work together to form complex networks that generate everything we feel, think, and perceive. From this perspective, consciousness is simply what happens when the brain reaches a certain level of complexity, but this explanation does not completely solve the mystery. The hard problem of consciousness, as posed by philosopher David Chalmers, is the question of how and why subjective experience, the feeling of consciousness, arises from purely physical processes. Why does a particular arrangement of neurons produce a vivid inner world of visual images, sounds, emotions, and thoughts? The gap between the physical functioning of the brain and the richness of conscious experience remains one of the most puzzling questions in science and philosophy. Some argue that consciousness is not just a byproduct of matter, but something far more fundamental. Some theories suggest that consciousness may be interwoven into the very fabric of reality, just like space and time. This idea, known as panpsychism, states that consciousness is not limited to humans or animals, but is a basic property of all matter that permeates the universe to some extent. Therefore, if consciousness is fundamental, it could mean that the universe itself has consciousness to some extent. This shifts the question from how the brain produces consciousness to how consciousness manifests through matter. This, in turn, suggests that the distinction between mind and matter may be artificial, that consciousness and the material world are deeply interconnected. Other theories offer a more traditional approach. Consciousness is an emergent property. According to this point of view, the complexity of the brain creates consciousness in the same way that water arises from individual molecules of hydrogen and oxygen. According to this point of view, consciousness depends completely on the physical structure of the brain. When the brain stops working, consciousness disappears. However, this explanation still does not answer the fundamental enigma of subjective experience. Philosophers and scientists have debated the true nature of consciousness for centuries. Is it reducible to material processes, or is it something more, something that perhaps escapes our current understanding of physics and biology? If consciousness plays a role in shaping what we perceive as reality, could it be that our subjective experience is not just a reflection of reality, but part of its very foundation? Ultimately, the nature of consciousness remains one of the greatest mysteries. What is it about consciousness that distinguishes it from everything else in the universe? Is consciousness a window into a deeper level of reality, or just a byproduct of complex physical systems? The question of where you are, where consciousness fits into the great fabric of existence, remains an unanswered question. The more we learn about the brain and the universe, the clearer it becomes that reality may be much more complex than we currently understand. Perhaps someday discoveries will prove that consciousness is not just something that happens within reality, but a fundamental key to understanding reality itself. For centuries, we have contemplated the night sky, listening to the stories that the distant stars tell us. We have built telescopes to see deeper and farther, to discover the secrets hidden in the cosmos. But light is only part of the story. There is another, more subtle language that the universe speaks, a language of waves and echoes written in the very fabric of space and time. Welcome to the era of gravitational wave astronomy. Gravitational waves are waves in the fabric of space-time, predicted more than a century ago by Albert Einstein. Unlike electromagnetic waves, such as light, radio, or X-rays, which are vibrations of electric and magnetic fields, gravitational waves are distortions in the very structure of space and time. They are created by some of the most violent and energetic events in the universe. Einstein's general theory of relativity, published in 1915, proposed that massive objects such as stars and planets do not simply exist in space, but deform and curve it. This distortion is what we perceive as gravity. But Einstein went further and suggested that when these massive objects accelerate, move, collide, or explode, they create waves in space-time, much like a stone thrown into a pond creates waves on the surface of the water. Gravitational waves are produced by cataclysmic events, collisions of black holes, supernova explosions, or the merging of neutron stars. These waves travel through the universe at the speed of light, carrying information about the events that created them. They tell us about the nature of gravity, the properties of black holes, and the birth of stars. But gravitational waves are incredibly weak when they reach us, after having traveled billions of light years through space. Detecting them requires instruments of unprecedented sensitivity, machines capable of measuring changes in distance smaller than a fraction of the width of a proton. This is the challenge that scientists have faced for decades. In the 1990s, a new generation of scientists set out to build such an instrument. The result was LIGO, the Laser Interferometer Gravitational Wave Observatory, which consists of two massive detectors, one in Washington and one in Louisiana, designed to detect these faint ripples in space-time. Its construction signaled a new era in the search for gravitational waves. Gravitational waves not only cross the vast expanses of space, but also cross through us. As these waves travel through the universe, they stretch and compress the space they move through, changing the distances between objects. But the question arises, do gravitational waves stretch us too? In theory, yes, gravitational waves stretch and compress everything in their path, including us. However, the effect is incredibly small. A passing gravitational wave would stretch you less than the size of an atomic nucleus. It is so small that it cannot be perceived or noticed by us in any way. LIGO, the most precise measuring device in the world, uses a laser interferometer to detect these tiny changes. The device divides a laser beam and sends the two halves through perpendicular arms several kilometers long. When a gravitational wave passes, it changes the length of these arms minutely, altering the interference patterns of the light. This change indicates that a gravitational wave has passed through. Thus, although gravitational waves stretch us, their effects are so tiny that they can only be detected with advanced technology, such as the LIGO instruments. Through these ultra-precise measurements, we can hear the faint whispers of the universe. Gravitational waves are not only distortions in space-time, but they also transport energy. When massive objects such as black holes merge, they release an enormous amount of energy as gravitational waves. This energy travels through the cosmos, rippling through space-time and revealing the most powerful events in the universe. The first detection by LIGO in 2015 confirmed that these waves carry energy from their source, causing black holes to spiral closer and eventually merge. The amount of energy transported by these waves is astonishing. In just a fraction of a second, the merged black holes emitted more energy than all the stars in the observable universe. This discovery not only confirmed Einstein's theory, but also opened a new avenue for understanding the most energetic processes in the universe, revealing information about the objects and events that created them. Each detection tells a story about the formation and evolution of black holes, neutron stars, and even galaxies. The energy transported by gravitational waves not only stretches space, but allows us to map the most extreme environments in the universe and understand how black holes and neutron stars form, as well as explore the very nature of space-time. Gravitational waves not only affect the space they move through, but also have profound effects on the objects that create them. When two massive objects such as black holes merge, the gravitational waves they emit transport significant energy. This loss of energy directly affects the movement and structure of the black holes themselves. When neutron stars collide, the effects become even more dramatic. Gravitational waves not only strip energy, but also determine the final outcome of the collision, whether more massive neutron stars form, or whether the stars collapse into a black hole. These waves provide clues about the internal structure and composition of these dense, enigmatic objects. The gravitational waves we detect are signals from the heart of cosmic violence that reveal the forces at play, the incredible energies involved, and the ultimate fate of these cosmic giants. They help us understand how stars live and die, how black holes are born, and how matter behaves in the most extreme environments. To detect gravitational waves, scientists had to build an instrument unlike any other, the Laser Interferometer Gravitational Wave Observatory, LIGO. Its design is based on a simple but powerful idea: to use light to measure the smallest distortions in space. The principle behind LIGO is simple in concept, but complex in its execution. A powerful laser beam is split in two, sending each beam along two long arms, each 4 kilometers long. At the end of each arm, mirrors reflect the light back to the central beam splitter, where the two beams recombine. In the absence of a gravitational wave, the beams cancel each other out perfectly due to their carefully calibrated trajectories. However, when a gravitational wave passes through the Earth, it stretches space in one direction while compressing it in the perpendicular direction. This changes the length of the arms, altering the time it takes for the laser beams to return and creating a distinctive interference pattern that LIGO detectors can measure to detect these incredibly small changes. LIGO must operate under extreme conditions. The entire interferometer is housed in ultra-high vacuum tubes to remove air molecules that could scatter the laser light. The mirrors are suspended by finely tuned systems that isolate them from ground vibrations caused by traffic, wind, or distant earthquakes. LIGO was not alone in its quest to detect gravitational waves around the world. A network of observatories works together to listen to the universe, combining their data to improve the accuracy and reliability of detections. Virgo, located near Pisa, Italy, is the European counterpart to LIGO, with its 3-kilometer arms. Virgo uses the same principles of laser interferometry to detect gravitational waves in collaboration with LIGO. Virgo helps precisely locate cosmic events, allowing astronomers to point their telescopes to the right part of the sky at the right time. In Japan, the Kagra Observatory brings new innovations to the field. Located deep underground to protect it from surface noise, Kagra also uses cryogenically cooled mirrors to reduce thermal vibrations, making it even more sensitive to gravitational waves. By combining data from detectors on different continents, we can determine the location of gravitational wave sources with much greater precision. When a gravitational wave passes through the Earth, it arrives at each observatory at slightly different times. By measuring these time differences, we can precisely locate the origin of the waves in the sky. This global network has allowed us to carry out multi-messenger astronomy, in which gravitational waves are observed together with radio and gamma rays. Together, they paint a more complete picture of the most extreme cosmic events. Gravitational wave astronomy is truly a global effort. Scientists from all corners of the world are working together to unravel the secrets of the universe, demonstrating that in science collaboration knows no borders. Gravitational waves span a wide range of frequencies, and each frequency reveals a different story about the universe. LIGO and its associated observatories are tuned to capture specific frequencies that align with some of the most energetic events in the cosmos. LIGO is designed to detect gravitational waves in a frequency range from approximately 10 Hz to 10,000 Hz. This range is well suited to capture waves produced by events such as the fusion of stellar mass black holes or the collisions of neutron stars. These frequencies are within a range similar to that of the human ear, but instead of sound waves traveling through air, they are waves traveling through space-time. Each gravitational wave signal can provide information about the objects that created it. For example, the fusion of two black holes produces a chirp, a wave pattern whose frequency and amplitude increase as the black holes spiral closer, culminating in a sudden peak when they merge. The unique signature of each chirp allows scientists to determine the masses, spins, and distances of the merging objects. However, not all gravitational waves fall within the detection range of LIGO. Lower frequency waves, such as those produced by supermassive black hole mergers at the center of galaxies, are outside LIGO's current capabilities. The detection of these lower frequency waves requires different types of instruments, which is where the future of gravitational wave astronomy comes into play. The Laser Interferometric Space Antenna, LISA, whose construction is planned, will be placed in space to detect these lower frequency gravitational waves. By expanding our observation range, LISA will allow us to listen to the deep, slow rumbles of supermassive black hole mergers and other cosmic phenomena, which will further expand our understanding of the universe. By expanding the range of detectable frequencies, new windows to the universe will open, allowing discoveries ranging from the sharp chirps of neutron star mergers, laughter, music, to the low-frequency grunts of colliding supermassive black holes. Each new frequency band brings new opportunities to understand the cosmos. In August 2017, a revolutionary moment took place in astronomy. For the first time, an astronomical event was observed both in gravitational waves and in electromagnetic radiation. This event, known as GW 170817, marked the dawn of multi-messenger astronomy. GW 170817 was the fusion of two neutron stars, the remnants of massive stars that had previously exploded as supernovas. As these neutron stars spiral together, they emit gravitational waves detected by LIGO and Virgo. Only 17 seconds later, NASA's Fermi Gamma Ray Space Telescope observed a burst of gamma rays that pinpointed the event's location in the sky. This unique observation triggered an unprecedented global effort. Within hours, dozens of telescopes around the planet began observing the region at different wavelengths, from radio waves to X-rays, allowing scientists to study the event in detail as never before. This joint observation provided crucial information about the functioning of the universe. It confirmed that neutron star mergers are key locations for the production of heavy elements, such as gold and platinum, and their dispersion throughout the cosmos. This is a theory that had long been suspected and has now been demonstrated with direct evidence from gravitational waves. The discovery of GW 170817 demonstrated the immense power of combining gravitational and electromagnetic wave observations, allowing us to witness cosmic events with greater clarity and precision. It opened a new window to the universe, where each detection tells a richer, deeper story. Multi-messenger astronomy represents a new era of discovery in which light and gravitational waves combine to illuminate some of the deepest mysteries of the cosmos. Gravitational wave astronomy is still in its infancy, but its potential is enormous. What could we discover in the coming years and decades? What new mysteries of the cosmos could we solve with more sensitive detectors and more powerful instruments? Perhaps we can soon detect gravitational waves from sources we have never observed before, or we could hear the faint echoes of the Big Bang, confirming theories about the earliest moments of the universe. The detection of these primordial waves could provide direct evidence of cosmic inflation, the rapid expansion of the universe moments after the Big Bang, and could answer questions about the fundamental forces that shape the cosmos. Gravitational wave astronomy could also reveal unknown phenomena, objects, or events that we have never imagined. Exotic forms of matter, hidden dimensions, or the mysterious dark matter that makes up most of the mass of the universe. Gravitational waves could help unravel these elusive secrets. We are about to answer some of the deepest questions that have been asked about our universe. Gravitational wave astronomy offers a new way to explore the cosmos, paving the way for discoveries beyond our wildest dreams. The universe is full of whispers, and we're just beginning to listen. Imagine an explosion of energy so powerful that it eclipsed an entire galaxy for a moment, an explosion of unimaginable power that traveled billions of light years to reach us, whose origin remains a mystery. This is not simply science fiction. It is the real story of gamma ray bursts, the most energetic phenomena known in the universe. On October 9th, 2022, two astronomers discovered something unprecedented, the brightest gamma ray burst of all time, which they nicknamed BOAT. It was so unusual that it shook almost all their previous concepts about these cosmic phenomena. But the story of GRB 221009A is not limited to its brightness, nor is it about the questions it raises, the anomalies in its spectrum, the unexpected absence of heavy elements, and the new challenges it poses to our understanding of how the most powerful explosions in the universe occur. What caused this colossal explosion, and what secrets can it reveal about the forces that shape our universe? The universe is a realm of unusual phenomena, some of which challenge the very limits of our understanding. Among them are gamma ray bursts, or GRBs, some of the most powerful and mysterious explosions known to science, discovered by chance in 1967 by U.S. military satellites. At first, gamma ray bursts were a puzzling mystery and cause for concern due to their intense release of energy, which was mistaken for nuclear tests. However, when it became clear that their origin was somewhere in the cosmos, GRBs quickly went from being a top-secret mystery to one of the most studied astrophysical phenomena. These bursts are divided into two main types: short GRBs, which last less than 2 seconds, and long GRBs, which can last up to several minutes. This division is not merely academic, but reflects different underlying physical processes. Short GRBs are usually associated with neutron-star collisions, while long GRBs, such as the one observed in October 2022, are associated with the cataclysmic collapse of massive stars. The event in question, dubbed the brightest of all time, or BOAT, occurred in the constellation Sagitta and was detected on October 9, 2022. This gamma-ray burst was unlike anything astronomers had observed. Its brightness, 10 times greater than all previously recorded GRBs, shocked the scientific community. What made this event even more surprising was its duration. It lasted 10 minutes, and the afterglow was visible for over 10 hours. Most explosions disappear from sight in seconds or minutes, making the BOAT an exceptional event. But beyond the spectacle, the BOAT event has profound implications for our understanding of the universe. Gamma-ray bursts are, by nature, windows into extreme conditions that cannot be replicated on Earth. They allow scientists to investigate the fundamental laws of physics, especially when matter is subjected to intense energetic and gravitational forces. The BOAT event, so bright and close, provided a unique opportunity to study these extreme conditions in detail. The data obtained opened new avenues for understanding not only gamma-ray bursts, but also the processes that govern the life and death of stars. The brightest of all time, GRB 22-1009A, stood out not only for its amazing intensity, but also for its incredible duration. The explosion was so powerful that it was the brightest gamma-ray burst ever recorded, lasted 10 minutes, and left a visible afterglow for over 10 hours. Such an event, only 2,400 million light-years away, is rare, almost unprecedented, as it occurs only once every 10,000 years. What makes this explosion truly unique is the combination of extreme brightness and prolonged visibility. Most GRBs are fleeting and are often only detected for seconds or minutes. Instead, the GRB 22-109A lasted much longer. High-energy emissions lasted for tens of thousands of seconds. This duration provided an unprecedented opportunity to perform observations and analysis across a wide spectrum of wavelengths, from X-rays to gamma rays. The brightness of the BOAT was so intense that it caused saturation effects in many scientific instruments, including the GBM Gamma Burst Monitor and the LAT Large Area Telescope. These instruments, designed to capture and analyze high-energy photons, were overwhelmed by the event, causing significant noise and delays in the data. In particular, the 400 GeV gigaelectronvolts photon was detected almost 10 hours after the initial burst, indicating unusually high energy levels despite its brightness and duration. This event also posed significant challenges for us. Spectral analysis shows that the maximum energy reached about 15 megaelectronvolts at the beginning of the event, gradually decreasing over time. However, part of what puzzled scientists was the discovery of a supernova related to the BOAT, which turned out surprisingly ordinary given the extreme nature of the GRB. One would expect its progenitor supernova to be equally extraordinary, but the supernova detected turned out to be almost completely unremarkable and even lacked signs of heavy elements, which are usually associated with such powerful explosions. But there is more about that later. This unexpected discovery has led to several hypotheses, one suggesting that the relative position of the Earth with respect to the GRB may have played a crucial role in the concentrated detection of gamma rays. The narrow jets emitted during the explosion probably pointed almost perfectly toward the Earth, which made the event appear much more intense than if the jets were slightly off-axis. This alignment, combined with the power of the GRB, created the perfect storm that resulted in BOAT being recorded as the brightest GRB ever observed. In addition, the detection of such high-energy photons raises intriguing questions about the radiation mechanisms that conventional models do not fully explain the unusual energy levels observed, leading some researchers to consider the possibility of new physics, such as interactions with dark matter particles. Although these ideas remain speculative, they highlight the potential of GRB 22-109A to expand our understanding of the universe in directions we do not yet fully understand. The formation of gamma-ray bursts is closely related to the life cycle of massive stars. When a star several times more massive than the Sun exhausts its nuclear fuel, its core can no longer support the weight of the outer layers. This catastrophic collapse results in a supernova explosion, but in some stars, it also leads to the formation of a dense black hole. When matter from a collapsing star falls into a black hole, strong magnetic fields convert some of that matter into narrow, concentrated jets that shoot outward at nearly the speed of light. These jets are the engines of gamma-ray bursts, and their orientation with respect to Earth determines whether we can observe GRBs. In the case of the boat event, the jets were particularly narrow and pointed almost directly toward Earth. Normally, the jets of the GRBs scatter a bit as they travel through space, but in the case of the boat event, the jets remained exceptionally concentrated, focusing their enormous energy on a relatively small area, resulting in a more intense emission. The influence of these jets extends far beyond their place of origin. When 22109 erupted, its intense gamma rays reached Earth and interacted with our planet's atmosphere in surprising ways. One of the most significant effects was a temporary compression of the ionosphere, a layer of the atmosphere that contains a high concentration of ions and free electrons. This compression was similar to the effect caused by a large solar eruption when the ionosphere is bombarded by solar particles, causing communication systems and satellites to malfunction. However, the gamma rays from the boat event were much more energetic than those normally associated with solar flares. The energy of the explosion was sufficient to cause noticeable changes in the ionosphere, even at altitudes where such interactions rarely occur. Observatories around the world quickly detected these changes, leading to frantic data analysis to understand the full impact of the GRB on Earth's atmosphere. The data collected during this event has provided scientists with new insights into how these explosions can affect planetary atmospheres, especially the interaction of high-energy photons and their potential to affect atmospheric chemistry and dynamics at the chemical level. Gamma rays triggered reactions in the atmosphere that produced additional nitrogen oxide and other reactive nitrogen species. These molecules play a fundamental role in ozone chemistry, especially in the destruction of ozone in the upper atmosphere. Although the exact effect that the boat had on global ozone levels has not yet been studied, such explosions may contribute to local or temporary changes in ozone concentration, which could affect the atmosphere's protection against harmful ultraviolet radiation. However, these observations have also raised further questions. The unprecedented strength and narrowness of the boat event jets challenge existing models of GRB formation and propagation. Standard models predict a certain degree of dispersion of the jets, which helps to distribute the energy over a wider area. But the jets of the boat event have refuted these expectations, suggesting that, under certain conditions, the jets can remain highly concentrated at much greater distances than the distances expected. According to current ideas, the extreme energy and rapid rotation of the collapsing star played a key role in this phenomenon. The intense magnetic fields produced by the rotation of the star likely contributed to the formation of the jets, preventing them from dispersing into space. In addition, the absence of significant interference from surrounding matter may have allowed the jets to maintain their narrow concentration over great distances. These findings not only challenge our current models, but also point to the possibility that there are GRBs not detected until now, with equally concentrated jets that have gone unnoticed by our instruments due to their directional nature. A better understanding of these mechanisms could reveal new GRB classes and their possible impact on both the local environment and distant planets, including Earth. However, let's return to the question of how our explosion relates to the formation of elements in the universe. It's simple. The formation of elements in the universe is history written in the hearts of stars. Inside a star, nuclear fusion works like a cosmic forge, converting light elements, such as hydrogen and helium, into increasingly heavier ones. This process continues until iron forms. At this point, the fusion process no longer releases energy, but requires more energy than it produces, leading to a catastrophic imbalance. The star can no longer support its weight, leading to its final collapse and, often, to a supernova explosion. While fusion in stars easily produces elements up to iron, far more extreme conditions are required to create elements heavier than iron, such as gold. These heavier elements are mainly formed by a process known as rapid neutron capture, or the R process. During the R process, the dense environment with a high neutron flux allows atomic nuclei to rapidly capture neutrons, creating increasingly heavier elements in a very short time. This process is best known in neutron-star collisions, where the enormous energy and neutron-rich environment create ideal conditions for the R process to occur. However, neutron-star collisions are not the only cosmic events that can produce heavy elements. Another potential site for our nucleosynthesis process is the collapse of massive stars that rotate rapidly and become black holes, events known as collapsars. In these scenarios, intense magnetic fields and rapid rotation can drive powerful jets that contribute to the R process, potentially creating significant amounts of heavy elements like gold and platinum. But when scientists pointed their instruments at the boat event, they were surprised to notice that something was missing despite the extreme energy and seemingly conducive conditions for nuclear synthesis. No signs of heavy elements formed in the R process were detected in the supernova spectrum. No gold, no platinum, nothing expected from such a powerful event. This absence raises important questions about our understanding of how and where the heaviest elements in the universe form. This surprising result leads us to think that not all collapsars are prolific producers of heavy elements. Perhaps the conditions necessary for significant nucleosynthesis in the R process are even more specific than we thought and only occur under certain conditions. These events, already rare, could mean that other processes or conditions related to neutron star mergers play a more important role in enriching the universe with heavy elements. Another interesting aspect of the brightest of all supernovas is that it could shed some light on the nature of dark matter. According to an intriguing hypothesis, dark matter could be made up of particles called axions, hypothetical particles that have not yet been directly observed. The idea that photons, particles of light, can be converted into axions as they travel through space is very tempting. If true, it could help explain why dark matter is so difficult to detect. Perhaps it is hiding in plain sight in the form of photons that can be converted into axions and elude our instruments. The boat event, with its intense burst of gamma rays, offers a unique opportunity to explore this hypothesis, as these gamma rays propagate through the vastness of space, and some may have interacted with cosmic magnetic fields. If they convert to axions, this process could reduce the flux of gamma rays reaching Earth, a subtle signal that could indicate the presence of axions. Although no definitive evidence of axions has been found in the boat event data, this possibility remains an interesting avenue for future research. If future observations of this type of event reveal patterns consistent with the conversion of photons into axions, this could represent a major advance in our understanding of dark matter and open the door to new physics beyond the Standard Model. Looking ahead to the future of astrophysics, the study of gamma-ray bursts remains a cutting-edge frontier full of promise and mysteries. Current missions, such as the NASA Gamma-Ray Space Telescope and the European Space Agency's COSY mission, continue to play a fundamental role in directing and analyzing GRBs, but the next generation of missions will push these limits even further. Projects such as the SV mission of the French COF and the next COSY mission of NASA are designed to integral of the European Space Agency, continue to play a fundamental role in the direction and analysis of GRBs, but the next generation of missions will further expand these limits. Projects such as the French SV mission and the next NASA COSY mission are designed to provide an unprecedented view of the high-energy universe. These missions will aim to detect the most extreme cosmic events and will allow us to collect data with greater precision, which could reveal new aspects of physics and deepen our understanding of the mechanisms underlying these powerful explosions. Our future may reveal the elusive nature of axions or perhaps identify the specific conditions under which the heaviest elements form. These are the questions that define the next steps in the exploration of the universe, and guide us towards a deeper understanding of the cosmos and our place within it. Events like BOAT are milestones in the development of astrophysics and remind us that the universe is far more complex and dynamic than we currently understand. Each discovery forces us to ask new questions and drives our search for knowledge, and, who knows, perhaps the answers to these mysteries are only a cosmic explosion away, waiting to be discovered by curious minds. In the meantime, we will continue to keep you updated on the news. Keep your curiosity, and until next time, you will surely know that black holes can be so massive that they can eclipse entire galaxies, but some are so mobile that they wander through the Milky Way like cosmic ghosts, undetectable, of course. Perhaps you are confused or even fascinated by the fact that the black hole closest to Earth is not as far away as you think. And when these cosmic giants collide, they generate frequencies as unique as fingerprints, frequencies that may hold the key to unlocking the deepest mysteries of the universe. But did you know that these waves interact in a much more complex way than we had ever imagined? Prepare for an extraordinary journey as we begin to delve into the mysteries of black holes, the truly enigmatic titans of the universe. Music in the cosmic pattern. Black holes are weavers of riddles and paradoxes. Although we are familiar with the small black holes, the remains of dying stars, and the supermassive ones that lurk in the hearts of galaxies, there's an enigmatic class that eludes our telescopic gaze: intermediate mass black holes. The Hubble Space Telescope, our eye in the sky, recently focused its attention on Messier 4, the closest globular cluster to Earth. What it discovered was nothing short of revolutionary: a black hole with a mass about 800 times greater than our Sun. This celestial object is located somewhere between 6,000 and 7,200 light-years from us. Why is this so important? Well, for years astronomers have struggled with a gap in the black hole family tree. We have evidence of both the existence of small black holes, with a mass equivalent to a few times that of our Sun, and supermassive black holes, with masses of millions or billions of solar masses. But intermediate mass black holes turn out to be the missing link, mysterious relatives that everyone has heard of but no one has ever seen. An equally interesting question is how these intermediate mass black holes form. One theory suggests they could be the nuclei of dwarf galaxies that lost their outer stars when merging with larger ones. Another theory states that they could form from the collision and fusion of smaller black holes. Identifying these elusive black holes is no easy task, requiring a symphony of scientific instruments, from X-ray observatories to precise calculations based on the movement of surrounding stars. The Hubble Space Telescope, with its unprecedented resolution, has played a key role in this discovery. The presence of a black hole affects its cosmic surroundings. By studying the gravitational choreography of the stars orbiting this massive object, scientists have estimated its mass. It is like understanding the character of an invisible puppeteer by observing the puppets dance. The discovery of intermediate mass black holes could rewrite the cosmic narrative. They could be key elements in the formation of galaxies and even hold clues about the mysterious dark matter that makes up most of the universe. In a cosmic world where distances are often incomprehensible, the term neighbor takes on new meaning. While our closest celestial neighbor, the Moon, is only 238,857 kilometers away, it is thousands of light years from Earth. But what does that proximity mean in the context of black holes, and why is it important in 2020? The European Southern Observatory, ESO, made headlines when it announced the discovery of a black hole in the HR 6819 system, located just 1,000 light-years away. This would make it the closest black hole to Earth, but this claim was later refuted by subsequent research by Abigail Frost from the University of Louvain, Belgium, who discovered that HR 6819 does not contain any black hole, but rather a double star system in which one star absorbs the mass of the other, a process known as stellar vampirism. This discovery was more than just a correction, as it opened new possibilities for studying stellar evolution and interactions after the expulsion of HR 6819. The title of closest black hole to Earth then became Gaia BH1. This black hole was discovered by the Gaia Space Observatory, a mission of the European Space Agency, ESA. Gaia's main task is to map the Milky Way in unprecedented detail, and it was thanks to this meticulous work that Gaia BH1 was discovered as the closest black hole to Earth. Gaia BH1 offers a unique opportunity for scientific observation and research. Its relative proximity allows for more detailed measurements and can help answer fundamental questions about the properties of black holes, such as their mass, rotation, and behavior near their event horizons. The study of black holes like Gaia BH1 relies on several observational instruments, from X-ray observatories to radio telescopes. Each instrument represents a piece of the puzzle. The closer a black hole is, the more precision these instruments will have to measure its properties, offering a more complete picture of these mysterious objects. Beyond its scientific importance, the idea of a nearby black hole captivates the public's imagination, makes the cosmos more personal, and provides a tangible focus for education and outreach. The story of Gaia BH1 can serve as a gateway to astronomy and astrophysics, enriching our collective understanding of the universe. In the cosmic theater, black holes often play the role of mysterious villains lurking in the center of galaxies or in double star systems. But what happens when a black hole is left wandering the universe alone, unconnected to any star or galaxy? What makes these black holes go rogue? And how do astronomers manage to find such elusive objects? Let's delve into the mysterious world of wandering black holes. The scientific community was thrilled when astronomers announced the first unequivocal discovery of a wandering black hole located 5,000 light-years from Earth. This black hole weighs 71 times the mass of our Sun and moves at an astonishing speed of about 28 m per second. The key to this revolutionary discovery lies in a phenomenon predicted by Einstein's general theory of relativity, known as gravitational lens. When a massive object, such as a black hole, passes in front of a background star, its intense gravitational field deflects the light from that star. This creates a brief brightening phenomenon, which is how this wandering black hole was discovered. As we know, the birth of a wandering black hole is a dramatic event. When a massive star exhausts its nuclear fuel, its core collapses and causes a supernova explosion. The energy release can be so enormous that it ejects the newly born black hole from its stellar cradle, sending it on an endless journey through space. This is how our newly discovered wandering black hole probably began its cosmic odyssey. What is even more intriguing is the speed at which this wandering black hole travels, about 28 m/second, a very high value in relation to the nearest stars. This speed is probably the result of the impact of a dying massive star that sent it on its solitary journey. The discovery of this solitary black hole is only the tip of the iceberg in future missions, such as those of the European Space Agency's Gaia Telescope, and NASA's Nancy Grace Roman Space Telescope. Astronomers hope to find even more space travelers of this type. These future discoveries will not only increase the number of known wandering black holes, but also refine our theories about their properties and frequencies. Each galaxy is like a cosmic dance floor where stars, gas, and dust swirl in a complex choreography. At the center of this dance is a supermassive black hole that sets the rhythm and tempo for the entire galaxy. Research published in the monthly notices of the Royal Astronomical Society shows that galaxies and their central black holes grow together regardless of their location in the universe. Astronomers have long puzzled over the relationship between a galaxy's mass and its central black hole. Both seem to be aware of each other, even though the black hole is much smaller than the galaxy in which it resides. This relationship implies a deep, cosmic connection, a kind of cosmic codependency in which the growth of one affects the other. One intriguing question in astronomy is, what came first, the galaxy or its central black hole? The answer is still difficult to determine. However, what is clear is that a close connection was very quickly established on a cosmic scale, paving the way for complex interaction between growth and evolution. Let's delve into young, gas-rich galaxies, the cradle of giant black holes. These galaxies are cosmic nurseries packed with the raw material for star formation and black hole growth. Studies show that these galaxies, known as blue nuggets, have very high star formation rates. They feed on nearby gas streams that not only accelerate star formation, but also contribute to the rapid growth of their central black holes. When black holes feed, they become active. The surrounding gas heats up and emits powerful radiation. This heated gas is less likely to collide with the black hole, creating a feedback loop that stabilizes the size of the black hole. However, as the galaxy grows, it can push more gas towards the center, allowing the black hole to grow again. The relationship between galaxies and their black holes adjusts itself. If a black hole is too large for its galaxy, it grows slowly, and if it is too small, it catches up because of the abundance of gas and dust in the galaxy. Therefore, some galaxies defy the norm. These blue nuggets, despite their small size, have large central black holes. As these galaxies age, their star formation stops and they become red nuggets, retaining their enormous black holes. As we delve into the abyss of the black hole, it becomes evident that young, gas-rich galaxies serve as the birthplace of various phenomena related to black holes. Whether they are luminous black holes of intermediate mass that rush through space or the black holes closest to Earth, their origins often go back to these bright, young galaxies. Understanding the cradle of these cosmic giants helps us unravel the mysteries that black holes hold. Now let's look at something really rare. There's a situation in which black holes collide, and, in doing so, create a cosmic symphony of gravitational waves around them that vibrate in the very fabric of space-time. These waves, first detected by the Laser Interferometer Gravitational Wave Observatory in 2015, opened a new frontier. However, recent research shows that these waves interact in common, complex ways as they propagate, which tests our understanding of gravity and the general theory of relativity. Traditionally, scientists have used linear models to describe these waves. However, a new study revealed nonlinear effects that reveal a more complex picture, similar to the difference between a calm pond and a rough sea. In a calm or linear pond, throwing a stone creates an isolated wave, while in a stormy or nonlinear sea, multiple forces interact to create complex wave patterns. When black holes collide, they emit unique frequencies or music chirps. These sounds are like individual notes in our cosmic symphony, each of which tells us something about the properties of the colliding black holes. They offer a new way to test the limits of the general theory of relativity and may even provide clues to the nature of dark matter. Recent discoveries have shown that pairs of black holes and dwarf galaxies are in the process of collision. These dwarf galaxies attract gas that feeds their black holes, causing them to grow before they merge. This process is a microcosm of the larger universe, where galaxies and their central black holes grow together. These colliding dwarf galaxies offer a vision of the early universe, which was full of similar small galaxies. Most of them ended up merging to form larger galaxies, such as the Milky Way. Understanding these processes helps us reconstruct the cosmic mystery of the formation of galaxies and black holes. As we delve into the abyss of black holes, we discover that each type, from luminous intermediate mass black holes to wandering black holes that rush through space, plays a unique role in this great cosmic symphony. The next generation of gravitational wave detectors will likely deepen our understanding of these cosmic phenomena, and, of course, each discovery, from the frequencies they generate to the very nature of gravity, undoubtedly adds a new level to our understanding of the universe. As our telescopic eyes become sharper and computational models more sophisticated, who knows what other cosmic mysteries these giants of the cosmos will reveal? Imagine a particle so elusive that trillions of them pass through you every second without a trace. A particle born in the burning hearts of stars, in the cataclysmic collapse of a supernova, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we learn to listen to their whispers? By immersing ourselves in the realm of these ghostly particles, we enter the territory where the known meets the unknown, and where the smallest particles hold the key to the most important questions. The story of neutrinos begins in the early 1930s, when particle physics was undergoing a revolutionary transformation. It was a time when the universe revealed its secrets to those who dared explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem in beta decay, a type of radioactive decay in atomic nuclei. Energy seemed to disappear, contradicting the principle of energy conservation, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried by an undetectable particle? He tentatively called this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with a neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory that described this elusive particle and consolidated its place in the scientific lexicon. Let's travel back to the Cold War, an era in which science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the focus of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not limited to military power, but extended to the realm of science, where both sides sought advances that would give them an advantage. One of these stories is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been very involved in research on neutrinos, and his defection caused a great stir both in intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era and how research on neutrinos had become the object of international intrigue. This period was marked by secret experiments, some carried out in underground depths, in abandoned mines or remote places, where scientists tried to capture these ghostly particles. Neutrinos, although one of the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that it was long thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it does not exist. At this moment, trillions of them are passing through you undetected. 3 types or flavors of neutrinos are known: the electron neutrino, the muon neutrino, and the tau neutrino. Each is associated with a corresponding charge particle: the electron, the muon, and the tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, each associated with a corresponding charge particle: the electron, the muon, and the tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery, as it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can shift between these mass states, leading to a change in flavor. This discovery not only won the Nobel Prize in Physics in 2015, but also highlighted the gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also protagonists in some of the most dramatic processes in the universe. In the heart of a star, nuclear reactions generate enormous amounts of neutrinos that leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to leave a dying star, signaling the beginning of a supernova. These particles provide crucial information about the processes taking place in the core long before light escapes. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova. During this cataclysmic explosion, an enormous amount of neutrinos is produced, greater than the energy emitted by light. These neutrinos leave the supernova almost instantaneously, propagating through space, and some of them end up reaching Earth, allowing us to glimpse these distant violent ones. It is also speculated that neutrinos could be related to one of the greatest mysteries of astrophysics, dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino that does not interact with any known fundamental force except gravity, could constitute dark matter, the invisible mass that makes up most of the matter in the universe. Although this remains a field of intense research, the possibility that neutrinos can unlock the secrets of dark matter underscores their importance in our quest to understand the cosmos. Thus, the search for high-energy neutrinos has led scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica is the IceCube Neutrino Observatory, which scans the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events still shrouded in mystery. Recent research has begun to unravel this mystery, pointing to active galactic nuclei, or AGN, as significant sources of these high-energy neutrinos. AGN are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases enormous amounts of energy, often forming jets of particles at high speeds. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a possible source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the core of the galaxy, where a supermassive black hole hides behind thick layers of dust and gas. This discovery refuted the popular belief that these neutrinos can only be emitted by galaxies with bright quasars, such as blazars. The surprises do not end with NGC 1068. Subsequent studies revealed two other galaxies, NGC 4151 and NGC 3079, as possible sources of high-energy neutrinos. The findings strongly suggest that the environment surrounding supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of the origin of high-energy neutrinos. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors in the world. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to further push the boundaries of our knowledge. In Japan, the Hyperkamiokande is about to become a leader in neutrino detection. This huge underground detector, located in a cave dug especially for this purpose, will be filled with 260,000 tons of pure water. The goal is to capture the fleeting flashes of Cherenkov radiation that occur when neutrinos interact with water molecules, a technique perfected over decades of Japanese research. Meanwhile, in the United States, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will use a state-of-the-art time projection chamber in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map the properties of neutrinos in great detail. Although Hyper-K and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K relies on proven technologies and aims at the massive collection of data. DUNE, on the other hand, is based on innovative technologies that can reveal new aspects of the behavior of neutrinos. There's a lot at stake. Both projects seek to answer fundamental questions about the universe, like the origin of matter itself. One of the key research areas will be a phenomenon known as charge parity violation, which could explain why the universe is mainly composed of matter instead of antimatter. The violation of charge parity, CP, could be key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it by comparing the oscillations of neutrinos and their antimatter counterparts, antineutrinos, as they traverse space. These detectors can show if there's a fundamental difference in the behavior of matter and antimatter. But the race for CP violation is also a race against time. Hyper-K is expected to begin collecting data as early as 2027, which could give an advantage over Dune, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for the next few decades. The Standard Model of particle physics has long been considered one of science's most successful theories, as it provides a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more evident than in the study of neutrinos. These elusive particles, which hardly interact with other matter, have properties that extend the limits of our knowledge. One of the most important challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to have no mass, but the observation of neutrino oscillation, when they change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model, but that wasn't all. The consequences of the appearance of mass in neutrinos go beyond a simple revision of the model, as they suggest the possible existence of a new type of neutrino, the sterile neutrino. We have already mentioned it in passing, but here is the essential point. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos only interact through gravity. This makes them even more difficult to detect, but their existence could explain several mysteries in physics. If sterile neutrinos are shown to exist, they would not only call into question the completeness of the Standard Model, but would open the door to a completely new physics. This would require expanding the model to include these new particles, which could lead to a more unified theory of fundamental forces. Neutrinos could also provide clues about another profound mystery: the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter, but today we observe a universe in which matter predominates and antimatter is scarce. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter counterparts, antineutrinos, may behave differently. If neutrinos break this symmetry, this could explain why there is more matter than antimatter after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence of CP symmetry violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a journey of 185 miles, 300 kilometers, through Japan to the Super Kamiokande detector for almost a decade. Researchers have observed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may behave differently. This possible violation of CP symmetry in neutrinos could be the missing piece to explain why the universe is composed mainly of matter. However, the current results, although promising, are still not conclusive. The level of statistical significance needed to recognize a discovery in particle physics is 5 sigma, and the results of the T2K have only reached about 3 sigma, which means that, although the tests are solid, they are not definitive enough to really confirm the CP violation in neutrinos and reveal the secrets of antimatter. Scientists are turning to the next generation of neutrino detectors, Hyper-K in Japan and Dune in the United States, which are ready to take this research to the next level. These huge detectors will collect much more data with greater precision, being able to reach the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science. Why is there something instead of nothing? The study of neutrinos, once considered an obscure branch of physics, could end up being the key to understanding the very structure of our reality. To answer some of the most profound questions in physics, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or KATRIN, in Germany. The KATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny mass of neutrinos by analyzing the energy of the electrons emitted in this decay. Cochrane aims to establish an upper limit for the neutrino mass, extending the limits of discernibility. Cochrane has already made significant progress by establishing an upper limit for the mass of neutrinos of 0.8 electron volts, with a sensitivity of up to 0.2 electron volts. However, this may not be enough to determine the actual mass of the neutrino, which could be even smaller. This finding has triggered a global effort to develop alternative methods and experiments that can exceed Cochrane's capabilities. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays by electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a tiny amount of heat that can be detected with extremely sensitive equipment. Experiments with holmium-163 have already demonstrated very precise energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the experiment of Project 8, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could exceed the limits set by cosmological studies and provide crucial data on the actual mass of neutrinos. The search to understand neutrinos is not limited to one country or continent. It is truly a global effort. The challenges posed by these elusive particles have brought scientists together from all over the world, fostering collaboration beyond borders. As we await the first signals from the Japanese Hyper-K, which is already taking shape in a newly excavated cave, and await news from Dune, nestled deep in an old gold mine in South Dakota, the next chapter in our understanding of the universe has only just begun. Stay tuned as we travel to the frontiers of science. One discovery after another. You have probably heard of dark matter, that substance that makes up about a quarter of the universe, the ghostly puppeteer that pulls the strings of the galaxy without ever showing itself. But dark matter is just the tip of the iceberg. Imagine a universe in which the balance of gravity is tilted in mysterious ways, where stars and binary systems, two stars orbiting a common center, defy the laws established by Newton and Einstein. What if their equations were not definitive? Recent research suggests anomalies and deviations in the orbital dance of double stars that neither dark matter nor our current understanding of gravity can explain. Are we facing a paradigm shift? Is our vision of the cosmos not as stable as we thought? In the cosmic ballet, the stars are the padas that call our attention. But have you ever wondered how these celestial bodies form? It all begins in the dark and cold corners of a nebula, a vast cloud of gas and dust. Gravity plays a key role here, attracting the particles closer until they stop resisting gravity and merge, triggering a nuclear fusion reaction that gives rise to a star. However, the life of a star does not last forever. There comes a time when the nuclear fuel runs out and the star faces its demise. For massive stars, this ending is spectacular. A supernova explosion that eclipses entire galaxies, if only for a moment. These supernovas are not just cosmic fireworks. They're the forges of the universe. It is in the crucible of these explosions that elements heavier than iron are created. So the gold in your jewelry and the calcium in your bones are stardust, the remains of a supernova. But this is where the plot thickens. In a universe dominated by dark matter, these stars and their explosive depths are part of a larger scenario. Dark matter, with its gravitational force, influences the formation of galaxies and the distribution of stars within them. Imagine two galaxies, one with dark matter and one without. In the galaxy with dark matter, the gravitational forces are so strong that they can cause bursts of star formation, leading to a greater number of supernovas. In these galaxies, stars form and die at an accelerated rate, creating a dynamic and ever-changing landscape. Recent studies have quantified this relationship, showing a direct correlation between the amount of dark matter in a galaxy and star formation rate. But what if this correlation is not as simple as it seems? Enter the M theory, which modifies Newtonian dynamics. This theory suggests that gravity behaves differently at very small accelerations. If the M theory is correct, the high rate of star formation in dark matter-rich galaxies could have an alternative explanation: double star systems. Those cosmic pairs that we mentioned above can serve as an ideal test laboratory for these theories. Their orbital dynamics can show whether Newtonian gravity persists or whether man offers a better explanation. As scientists delve deeper into the data, especially the treasure that the Gaia mission has provided, we're getting closer to understanding the true nature of this galactic dance. In cosmic narratives, dark matter is often depicted as a silent, mysterious entity that shapes galaxies, but remains elusive. One of the most compelling theories that attempts to solve this mystery is the cold dark matter, or CDM, model. In the CDM model, dark matter is cold, meaning that its particles move much slower than the speed of light. This slowness allows them to cluster together to form the gravitational scaffolding on which galaxies are built. Computer models based on CDM have been very successful in reconstructing the large-scale structure of the universe. They show a cosmic network of galaxies connected by filaments of dark matter that is very similar to what we observe. But, as in any good story, there are unexpected twists. While CDM does an excellent job of explaining the grand architecture of the universe, it falters when we get closer to individual galaxies. Take, for example, the rotation curves of galaxies, the speed at which stars and gas rotate around the galactic center. According to Newtonian physics and the CDM model, this speed should decrease drastically as we move away from the center, but observations tell a different story. The rotation curves remain surprisingly flat, suggesting that there is something more involved, perhaps another type of dark matter or even a modification of gravity. And then there are the dwarf galaxies, smaller satellites of larger galaxies like our Milky Way. The CDM model predicts many of these dwarf galaxies, but we don't see as many as expected. These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing as many as expected? These inconsistencies have led scientists to consider alternatives and question the very basis of the CDM model. Could it be incomplete, or are we missing an important piece of the cosmic puzzle? This is where M comes into play again, offering a different set of equations that better explain these galactic characteristics. It is as if there were two different scripts for the same movie, each with its own interpretation of the main character, dark matter. The scientific community is divided. Is CDM the definitive theory that unifies our understanding of the universe, or just a step toward a more complete model? For centuries, Sir Isaac Newton's equations have been the basis for our understanding of gravity. They have been tested and repeated many times and have stood the test of time. But what if there is more? We present Theory M, where in some regions there were twists that led to the formation of cosmic strings. Cosmic strings, if they existed, would be incredibly thin, yet incredibly dense. A string less than an inch wide could weigh as much as Earth. They would extend along the vast expanse of the universe, perhaps even from one end to another. Due to their enormous mass, cosmic strings would exert a strong gravitational pull that would affect the movement of galaxies and even bend light. They could serve as cosmic highways that direct the flow of matter and energy throughout the universe. The search for cosmic strings continues. Scientists are using theoretical physics and observational astronomy to search for these elusive structures. If the existence of the strings is confirmed, they could become the missing links that help us understand not only how the universe is organized, but also why it is organized in this way. However,